So here's our problem. We have these basalt samples. They quite often don't have terribly useful datable phases like zircon or apatite. Sometimes they have phosphates, meryllites. And so what we want to do is try and extract an age. But the problem with the moon is that we know that the moon, probably related to its giant impact origin, suffered a profound volatile loss early in its history, and that included lead. And so generally we expect lunar mu values, which is the 238-204 lead, to be significantly higher than terrestrial reservoirs. So typically lunar we think of in terms of hundreds or thousands in this ratio, whereas terrestrial reservoirs are around 10 in the mantle, at 8. So lead in lunar samples is very radiogenic through time because there's no common lead. All you've done is generate radiogenic lead. And it's very sensitive to terrestrial contamination. Bring a sample back from the moon, take a lunar meteorite, leave it in the desert for a while, cut it with a saw, make a thin section, you've contaminated it, it's a disaster. And so lead isotopes typically have not yielded very good ages for lunar basalts over the years. There's always been this problem with terrestrial contamination. So just to give a background how we've done this type of work, you need to understand a little bit the systematics behind lunar lead isotopes. And what we do is we use a different form of the lead isotope diagram. This is the inverse lead isotope diagram, where we plot the 207-206 ratio against the 204-206 ratio, because very radiogenic compositions get compressed to the axis here. Now, our starting point is the solar system initial, which we believe is defined by the Canyon Diablo troilite lead. And also on here, I've plotted modern terrestrial lead, which is the one everybody uses, Stacy and Kramer's 1975 model. They're all roughly in this particular space around about here for modern. So how do we evolve? Well, if we take a mu of 10, here you see we roughly hit modern terrestrial lead from Canyon Diablo troilite through time. If we take a mu of 100, we end up going to very high ratios here on 7.6 and then ending up somewhere here. Present day, if we take mu of 500, even more extreme high ratios at some point and then ending up somewhere down here. Same for 1,000. And so we can define isochrons in here, 2 billion year isochron, 3.9 billion year isochron, 4.35 billion year. The systematics are fairly straightforward when you get your head around this diagram a little bit. Now, if we take a single example at 3.9 here, so here it evolves with, say, a mu of 500, the schematic example. At 3.9, it will be here, that's its initial. It will evolve to present day to this point here, which is about 0.4 on 7.6, which is 3.9 billion years. So we end up generating an array of samples somewhere along here. And this is actually an isochron itself. Or you could view it as a mixing line between the radiogenic component and the initial lead component. Same thing. Now, when people looked at lunar mare basalts and various volcanic glasses from Apollo 15, this is conventional work, bulk work. They just defined this area down here, and you can see it's pulling away from the axis here. So it's not a very nice set of data. It's very hard to define a good age here. And the problem with it is that when you have a system like this, you have an initial component here, you have a radiogenic component here, and then you have this terrible terrestrial, unavoidable terrestrial contamination component, which is generating a triangle towards modern terrestrial lead. And this is where SIMS comes in, because by using SIMS, we can avoid the places where the terrestrial common lead typically sits, and that is in cracks and grain boundaries, when you polish a sample, doesn't matter what you do, it's unavoidable that you will get common lead, terrestrial lead sitting in grain boundaries and cracks. So what we can do is avoid those areas, target the clean centers of grains, and then hopefully, instead of getting this set of horribly mixed data here, we reject these samples that are in the triangle approaching terrestrial contamination until we get a statistically valid curve along this axis here. And hopefully we define the initial composition here with some measurements, the low uranium measurements, and the higher uranium, more radiogenic phases will define the radiogenic point here. And we can put an isochron through typical standard isochron method and get an age. And here's what we've done. This is from a paper by my former postdoc, Josh Snape, together with Sasha Nemchin, who many of you probably know. And you can see that here's an Apollo 11 sample. We generated an age of 3687 plus or minus 4 million years. So these are rather precise. These points are obviously the ones we leave off. They're trending towards common lead. Here's another one. This is an Apollo 12 basalt, around about 3240 million years. Again, points that we've left off here. And here's another Apollo 12, and here's an Apollo 14. The Apollo 14 having somewhat more contamination here. Apollo 14 samples, if anybody works on them, are terrible. I don't know what happened. They're always more contaminated than the others. So what we can do, of course, we have the age and we have an initial up here measured on the least radiogenic phases. And so we can generate a curve here, a model where we take, in this case, from Josh's paper, we had 6 samples of Mare basalts and we had their mu values. We could calculate them back to the point they intersected. And this is a major differentiation event on the moon of about 4376 million years, plus or minus 18. We believe that's probably the formation of the Crete Reservoir. And then we can measure we can estimate rather. Speculate's coming. We can estimate back in time the mu value required to get from Canyon Diablo troilite to this differentiation point. And so our Mare basalts defined anywhere between about a uranium lead ratio of about 370 up to some of the Crete samples, which are up to almost 4,000. And this first stage, we have a mu of about 460, assuming an age of 4,500 million years. Now, that also potentially gives us a way to estimate the age of the moon, because the age of the moon is still strongly debated. And so if we look at the mu1 value, which is, we make 2 assumptions here. We have a simple 2-stage model, Canyon Diablo troilite, essentially being retained until moon formation, because we expect prior to moon formation a mu value of maybe 1 or 2, a little bit like we see on Mars. So that composition shouldn't go anywhere. So we can essentially move it. The composition stays the same, but we can assign any age to it. Assumption 2 is that the mu value of our mantle reservoirs cannot change, cannot decrease during the fractionation event. In other words, mu2, which is between the differentiation event and the sample extraction, which is defined by our initial ratio, is greater than or equal to mu1, which is the value between moon formation and differentiation. So we have to have this locus of curves for mu1 in green here, and here's our least radiogenic Apollo 11 sample. We know the moon can't be older than 4.51 billion years based on tungsten isotopes, and we violate this mu2 greater than mu1 at about 4.49, 4.50. So it looks to us as though the moon has to be around about 4.5 billion years. And that's this intersection here. Okay, I'm going to finish up by saying that, well, this only works if assumption 2 is valid. Now it's becoming clear that the uranium-lead behavior during magma and ocean crystallization might actually permit some basalts to have a lower uranium-lead ratio than their source. And so that's actually a problem for this older moon model here. This could still be valid, but if assumption 2 is not valid, then it's possible to allow younger ages than 4.5 for the age of the moon. This is something we're working on right now to try to define a little bit better in different ways. Okay, so I want to end there. Thank you again for the honor of giving this talk, and I want to wish you the best of luck with your new 1300. I think you've got a lot of fun science ahead of you. Thank you.